Everybody, video notes 11.1, and here we go. So I always start with what we're going to learn, and this is what we're going to learn. So chapter 17 is going to help you with this unit. I recommend that you read it. Okay. So what makes a reaction go? We already know that if a reaction is going to go towards products, it's because spontaneously, it's because entropy goes up and enthalpy goes down, and we get a negative delta G. But guess what? We don't always get a negative delta G. In fact, you can have a delta G of negative, which means spontaneous. That means reaction goes forward only. All right. If you have a delta G as a positive value, that means really the products would go towards reactants only. But what if delta G is 0? That's the case when maybe enthalpy is pushing forward, but entropy is pushing in reverse. Use a double-headed arrow because, or two arrows, one going forward, one going back, because it shows that both reactions are occurring at the same rate. Maybe heat's pushing that way, entropy's pushing that way. Okay, so what is equilibrium? Equal rates of reactions forward and backward. Just think of a bridge, okay? You got so many people over here, so many people over here. If you got cars going equal rates across the bridge, then you get the same number of people. The number of people over here doesn't really change because each time more people are coming in. The number of people over here doesn't change because each time more people are coming in. So if they're crossing at equal rates, the number of people on each side doesn't change. Now, they don't have to be equal, just their number doesn't change. If you have sugar on the bottom of your iced tea because you put too much in, all right, actually some's dissolving, but every time a little bit dissolves, some more precipitates, and so the amount that's dissolved stays constant, and it's because there's an equilibrium of dissolving, precipitating, dissolving, precipitating. So equilibrium, dynamic equilibrium. Dynamic means change. So what does dynamic mean? Change. So if I say, hey, what does dynamic mean? You'll say, it's change, Mrs. Harbin. Dynamic means change. So how can we have equilibrium but be changing? Okay, so right now the water's going in, but that water's coming out. So this amount in the cup stays constant, but what's changing is this is new water molecules. Those are old water molecules, but we have equal number of water molecules in the cup the whole time, except they're not always the same water molecules because it's always changing which water molecules they are. Same thing here. The rate going in is the rate going out. Concentration stays constant, amount stays constant, but it's not the same. It's different water molecules each time. Okay, so when you start a reaction, maybe the forward reaction goes at a certain rate, reverse goes at another rate, but when they start going at the same rate, that's when equilibrium is reached. Amount of reactants goes down, amount of products goes up. They reach equilibrium when this amount of each thing doesn't change anymore. Although we know it is changing the whole time, it's changing at equal rates. Okay, so because they're changing at equal rates, we have what you call an equilibrium constant expression. K, equilibrium constant expression. So in order to calculate K, you have to be able to write the expression first. So we're going to take the concentration of the products raised to the coefficient power. If there's more products, you take their concentration raised to the coefficient divided by reactants. Concentration and coefficient. So K is the equilibrium constant, R is for reactants on the bottom, P is for products on the top, brackets mean concentration. Hey look, it's a balanced equation of A's and B's and C's and D's. Alright, notice the state of matter here. Aqueous for all of them, so we can use them. So it's the concentration of substance C. Oh look, it's a product, a different product raised to the power. We did this with KSP. Reactant A, so it's products over reactants. They don't include values for pure solids. Do not put pure solids in a equilibrium constant or pure liquids. The concentration of solids and liquids don't change. What do I mean? Well, look at this. Here's a solid, right? This is the moles of solid per liters of solid is not going to change. All right? So its concentration doesn't change, so we don't put solids. No, if you see a solid, don't put it in. How about liquid? Same thing. Liquid is 100% concentrated. So it's not going to be changing in a constant rate. It's not going to be changing. So liquids are not put into a K expression. Okay, just leave them out. All right, so let's do some. All right, so what do? We do products, constant, we do products. Let's see, we have tin. Oh, but look, solids don't count. And we have zinc ions in our products and no coefficient, so we're fine. Over reactants. Zinc solid, sorry, you're not allowed. And tin ion concentration. So the equilibrium constant expression for this reaction would be that. Okay, what about this one? Alright, so we do products. Oh, it's a gas. Gases are allowed. Alright, because gases have volume per moles per liter, so we can do it. Chloride ions. Any coefficients? No, so no exponents. And then we have Na ions, and those are aqueous. And then, oh, sorry, not allowed. Alright, the equilibrium constant expression. Okay, oh, sorry, you're not allowed. Here's aqueous, plus 2 ions. Coefficient of 2, so we square that a bit. Alright, look at iodide ions. Coefficient of 2, square it. Hey, those are reactants, good. Times, there's no adding or subtracting in these equilibrium constant expressions. We have iron ions, just squared, second power. Okay, so it's always products over reactants. Use coefficients. Too bad solids and liquids you're not allowed. All right, so truth is not all reactions are at equilibrium, but if it's going to equilibrium, it's on its way. All right, so we can actually take the ratio of the products over reactants at any time, and we call it a reaction quotient because we're not sure if it's at equilibrium. We call it Q. Wait a second, this looks exactly the same as KEQ. That's true, but if we don't know if it's at equilibrium, it's called a Q for reaction quotient because we're not sure it's at equilibrium. So Q is a reaction quotient, because we don't know if it's at equilibrium, but we can use it to tell us if it is or not. How? Okay, well, if we look for a Q and it's equal to KEQ, then we're right on. We're already at equilibrium. That reaction is at equilibrium. But what if we get a Q that's bigger than the KEQ? Well, what does that mean? If Q is bigger than KEQ, that means, and remember it's products over reactants, then, and it's bigger than that, then guess what? We have too many products, so we have to shift towards reactants to get to equilibrium. Okay? If this number is bigger than what it's supposed to be, that means there's too much at the top, so we have to get more of the bottom. So we're going to shift that way. What if Q is less than KEQ? Well, products over reactant. If this number is too small, then it has to get bigger. How does it get bigger? Well, we need a bigger top number, so the reaction has to shift towards the products to get there. Okay, so if Q is not equal to KEQ, then it's on its way to equilibrium, and we can tell which way it goes because we know math. Yay, math rules. Woo. All right, so let's practice. Hey, they give us an equilibrium constant, so let's write an equilibrium constant expression. KEQ is equal to the products HI, and we have to square that because of 2, divided by the concentration of the reactants. We have I2 gas, no coefficient, H2 gas, no coefficient. That's the equilibrium constant expression. We're going to use it. Okay, it tells us that it's hey, the current concentrations of gases are known to be this. So right now it's a current concentration. It says, is it at equilibrium? Well, we don't know, so we call it a Q. We plug in HI is 0.58. Guess we have to do that. Square it. All right, concentration of sorry. Well, it doesn't matter which one's 44. Concentration of H2 is 0.81. We calculate that out, and we find out we get 0.94. What? 0.94? But the KEQ is equal to 7.1 times 10 to the second. So that means right now, this Q is smaller than that KEQ. So, what if not? So it's not at equilibrium. Is it at equilibrium? Nuh-uh, no way. All right, not yet. If not, which way will it shift? So Q is less than 7.1 times 10 to the second. It's less than 710. So, oh, train time. So this Q has to get bigger. What's the only way for this ratio to get bigger is if this number gets bigger. In order to get this number bigger, we have to shift towards the right, shift right. Okay? We can make something called an ICE table. I'm going to practice on this one with you so you can see what I mean by ICE table. An ICE table, the I stands for initial. Initial what? Initial amount. So the initial amount of H2 when we first start this is 0.81 molar. I2 initially is 0.44 molar. HI is 0.58 molar. So what does the I stand for in an ICE table? Initial. C is the change. The change that's going to have to happen. Well, we know we're not at equilibrium, so it's going to have to change. And when it changes, HI is going to have to get bigger. This is going to have to get bigger. So this is going to get bigger. How is that going to get bigger? Well, anytime this gets bigger, it's because this turns into it. So if we don't know a number, we always put X. But because this has a coefficient of 2, we're going to put 2x. We're going to call that 2x. So HI has to change by getting bigger by, we don't know how much, but we know it's 2x times. How is this going to change? Well, this has to get smaller. So it's going to be, it's going to change by losing some I2 and losing some H2. Why am I calling these minus x's? Because the coefficients, all right, are 1, 1, and 2. So if some of this goes away, you're going to get 2x of that. Some of this goes away, you're going to get 2x of that. So the change has to be some of these go away, and we get some of that to make the top number bigger. So at equilibrium, we're going to have 0.81 minus x for the amount of hydrogen, 0.44 minus x for the amount of iodine, and 0.58 plus 2x for the amount of hydrogen. Because then what you can do is you can plug these into here and solve. Okay? All right, another example. Hey, what if we had 4 moles of hydrogen iodide and we put them in a container that's 5 liters big, and then we heat it to 800 Kelvin? It goes to equilibrium. What will the equilibrium concentration of each species be? Let's start by writing what Kc equals 0.016, but Kc also equals, that's equilibrium constant, concentration of iodine, no coefficient, no thing, concentration of hydrogen over the concentration of HI. But let's check, are there any solids or pure liquids? Gas, 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 we're good. Okay, so basically we know this. We want to figure out the concentrations at equilibrium, each amount, because they tell us it's allowed to reach equilibrium. All right, so it's going to equal this constant at equilibrium, and these are the values. So what we have to do is figure out, well, what does it start at? Initial, remember ice, initial concentration, 0.8. Where do we get 0.8? We're 4 moles of HI divided by 5 liters equals 0.8 moles per liter, which is molar. Okay, 0.58 moles per liter. Okay, so that's why this says initially 0.8. When we first start, that's all we have is HI. So we have 0 H2 and 0 I2. C is change. Change. How's this going to change? Well, to get to equilibrium, some of this has to turn into those things. How much? We don't know. So we say minus. Minus how much? Well, we use the coefficient, minus 2x. So every time some of this turns into that, we're going to get some hydrogen. How much hydrogen? X amount of hydrogen. How much iodine? X amount of iodine. And it's going to increase, so it's plus. Right? Then the equilibrium concentration is going to be the change, the initial, together with the change is going to be how much we have at equilibrium. The initial together with the change is how much we have at equilibrium. Initial, change, equilibrium. So to figure out what the concentrations are, we have to plug them in to 0.016 is going to be equal to the concentration of I2, X. Concentration of H2 is X. I'm just plugging them here. And divided by 0.800 minus 2x. Wait a second, we have to square that. And so, if we want to know each concentration, we got to figure out x and plug them into here. Okay, so how do we figure out x in this case? Well, guess what, kids? We're going to have 0.016 equals x squared over 0.8 minus 2x times 0.8 minus 2x. Wait a second, Mrs. Harbin. Could this be, will this be a quadratic formula? You betcha. Woohoo, finally we get to use quadratic formula for a reason. Okay, so basically we got to move this over to this side, but I'm going to put it back as squared. So we have 0.016, x squared right here is going to be equal to 0.016 times 0.8 times 0.8 minus 2x squared. All right, and then we'd have to square, we'd have to break that out, get our first, outer, inner, last, do a whole bunch of fun stuff, and then solve for x. Okay, so we'll practice that in class using the quadratic formula to do that. Okay, We will, I promise. Okay, hey look, it's another problem. This time we have 0.6 moles of NO, 0.75 moles of O2, and we have a 2-liter flask. Alright, so we need molarity. So 0.6 moles of NO divided by 2 liters. What is that? 0.3. Alright, so this is 0.6 moles divided by 2 liters equals 0.3 molar. Alright, 0.75 moles divided by 2 liters equals 0.375 molar. Alright, it's in an empty flask, so there's nothing there. It goes to equilibrium, so we're going to get to equilibrium. What will the equilibrium concentration of each species be? Here's our balance equation. I don't know why that arrow got moved. And here's our constant. So, here's the balance equation. Let's call O2x. Alright, so that means NO is 2x, and NO2 is also 2x. But what's going to happen is that since we're starting with some of these two, to get to equilibrium, it's going to have to go towards reactants. We have no reactants. So some of this is going to go away, X amount, coefficient 1. Some of this is going to go away, 2X amount. So initially, here's what we have. What's the change going to be? Well, some of this is going to go away, that's minus X. Some of that's going to be minus 2X because the coefficient. There's a 2 and a 2 in the balanced equation. All right. And then if this is going away, this is forming, and there's 2 times, so it's 2x. And E is the equilibrium. Initial change equilibrium. At equilibrium, we'd have 0 plus 2x. We'd have 0.3 minus the 2x that changed into reactant. And this one is 0.375 minus the x that changed into reactant. Okay, so after all of that, you would get plug this into the equilibrium constant expression, and we know that Kc equals 0.5, which is going to be equal to the concentration of NO squared times the concentration of oxygen, no coefficient, divided by, so products over reactants, that's a bracket, NO2 squared. So then we plug these numbers in. That one goes in there, that one goes in there, and that one goes in there. And then you solve for x. Okay, and then once you solve for x, you figure out that, and that. Okay? Alright, hey, look, it's another problem. It's hydrogen gas and fluorine gas reacting to form hydrogen fluoride. We have 10 moles of H2 and F2 in a 1 liter container, and 4.5 moles of hydrofluoric acid are formed. What is the value of the equilibrium constant K? So we want K. What's K? So we want to find products, HF squared, over reactants, concentration of hydrogen times concentration of fluoride. Is there a plus sign there? No, these are all multiplying and dividing. Okay, so let's ice it. Ice baby. Here we go. Initially, for H2, we have 10 moles divided by 1 liter. We have 10 molar H2. All right. Initially, F2, we have 10 molar F2. Initially, HF, we have 0. All right. It's going to change, though. To get to equilibrium, we have to have sum of everything. And since we don't have any HF, we know that's the way it's got to shift. How's it? Hey, come back. How's it going to shift? Well, the H2 is going to change by X amount. The F2 is going to change by X amount. But the HF is going to change by 2X amount. So initially we have this. It's going to change. And then we'll get to equilibrium. So at equilibrium, we'll have the 10 molar we started with minus the X amount. We'll have the 10 molar of fluorine gas we started with. And then 0 plus 2X is how much HF will have. Okay. Hey, but look, there's something else in this problem that we didn't have in the others. We know that 4.5 moles of hydrofluoric acid are formed at equilibrium. Okay. So we do know this. We do know the equilibrium concentration. So the equilibrium concentration of HF is 4.5 moles for 1 liter. So 4.5 molar is equal to 2X. So X is going to be equal to 2.25 molar. So now we do know X. This is very, very fortunate, all right? Because now if we know that X is 2.25, we know that 10 minus X is the equilibrium concentration. So 10 minus X 10 minus 2.25 is 7.75. 7.75. This is also going to be 7.75. So guess what? We are saved. We can plug this in. We know that HF concentration is going to be, the concentration of HF is 0.45 moles per liter. Alright, so we got to plug that in. I said 0.45. We know it's 4.5 molar. Now you're saying, wait a second. Well, we use this to solve for X. But this is still going to be the concentration, 4.5 moles per liter. Then we solve for HF. We plugged in 7.75. The concentration of, I said HF. That's concentration of F2 is 7.75. And so when we're done multiplying, squaring that, dividing by that, we find out that the constant, the equilibrium constant, is 0.337. All right, so what's equilibrium? Okay, it's EQ is the abbreviation for equilibrium. Let's listen to a little. Okay, so EQ is the abbreviation for equilibrium. EQ is dynamic. That means the rate of the forward equals the rate of the reverse. All right, equal rates, not amounts. K is a constant that can only change with temperature. K is products over reactants. Raise the coefficients. No solids, no liquids in K. Q is products over reactants, but we don't know if it's at equilibrium, so we use it. ICE stuff, if you need to, mean figure it out by figuring out initial change in equilibrium if you have to. All right, we're going to practice. It's been fun. This song is for 6th hour and 4th hour because it's tons of fun. But you guys, please stick with me on this one. We'll keep practicing in class. But shout out to everybody I'm supposed to shout out to because I really don't remember. Peace out. Oh, hey, look. Pop-eyed Cow's reading the book. Oh, look, it looks like equilibrium. Do it. Peace out, folks.